Welcome. This lecture is about finding the center of mass of a system of masses, and they put this in this chapter involving conservation of momentum because if we think about a complex system of mass like a car, what we've been talking about so far is collisions. And so let's take this car right here. Let's say another car comes in and hits him, not at the center of mass, but hits him on the end right here. This guy's going to start rotating around and moving off in some direction. All right, so we've got like rotation and motion, translational motion moving from one place to another. But what we can say is, oh, here's the center of mass of the car. The center of mass of the car we can treat as all of the mass of the car being located right there, and it moves off in that direction, even though the other parts of the car are all rotating around it. And the center of mass of this car, even after the collision, even if he is rotating as well, he also, we can treat the center of mass of him moving off in some direction. And we can still say that the center of mass of the system is conserved. I'm sorry, the momentum of the center of mass of the system is conserved. So we're not going to get into motion of centers of mass too much, but we do need to be able to find the center of mass. So let's erase all this fun stuff here, and let's just talk about finding the center of mass. I didn't want to clear everything, just the annotations. There we go. All right, so let's talk about a really, really simple system that consists of two masses. Here's mass m, and here's the other mass m, and they are separated by a distance L. If the two masses are the same, then we know from experience that the center of mass is right here. And it's halfway between the two. All right, so let's talk about a little bit more complex system. Let's say that we've got a mass 2m here and a mass little m here. And what we know is that the center of mass is going to be somewhere closer to the 2m, than it is to the m. But we need a way of mathematically showing what this center of mass is going to be. All right, so the first step in any of these center of mass problems is you need to pick your origin, the place where your x and y coordinates are 0. So for this problem here, I'm going to put that place as my origin, 0, 0. And the way we find the center of mass of a system is we compare the total mass of the system to the masses and the positions of each mass in the system. All right, so here's how it's going to work. This mass here is a total mass little m, and it's situated a distance L away from the origin. And this mass here is a total mass m, but it's situated on the origin. So here's what the equation for the center of mass looks like. We say xcm is equal to the individual positions of the centers of mass times those individual masses divided by the total mass of the system. All right, so for the time being here, let's erase these two guys down here, and let's mathematically confirm that the center of mass of our system up here is indeed 1/2 L, or halfway between m, the two m's. All right, so we're going to apply the equation. So the x position of the center of mass, the x coordinate of the center of mass, is equal to the first mass. That's this guy over here on the left-hand side. His mass is m, and his position is 0 meters away from the origin, plus this mass over here on the right-hand side. He is a distance L away from the origin, and his mass is also little m. And we're going to divide by the total mass of the system, which is m plus m, little m plus little m, which gives us 2m. So simplifying here, 0 times m is just 0, and we have L times m divided by 2m. Masses cancel, and we do indeed get L over 2 as our center of mass. All right, let's do another example problem with the system that we had before. We've got mass 2m here, and now mass m over here. Again, they're separated by a distance L. And we pick our origin of our coordinate system. Let's pick this guy, 0, 0. The mass on the right-hand side is our origin. So plugging stuff into our equation, we've got x of the center of mass is equal to the position of the first guy, 0, distance from the origin, times his mass, little m, plus distance of the second guy. Now we're going over here to negative L. So we've got his mass, 2m, times negative L, according to the way that I've drawn my coordinate system. And we're going to divide it by the total mass of the system, m plus 2m. So again, 0 times m is 0. We've got negative 2ml divided by 3m. Masses cancel out, and we've got the x-coordinate of the center of mass is equal to negative 2/3 L. And that's not a big deal. The negative just means that we're over here. All right, this is 2/3 L, and this is 1/3 L. And let's go ahead and confirm that and show that it doesn't matter where we put our coordinate system. Let's put the coordinate system here, 0, 0, our origin. And then our center of mass, erasing these guys, is something slightly different. So let's say we've got a mass of 2m, and that is 0 units away from the origin, plus a mass of m, and he is now a whole L away, divided by the total mass of the system, which is 3m. So we've got 2m times 0 is 0, so that goes away. We have ml over 3m. m's cancel, and we have L over 3 for our XCM, which is the exact same place, L over 3, as we got for having our coordinate system on the right-hand side, which was negative 2/3 L. Okay, so negative 2/3 L is, this is an L right here, is the same as 1/3 L if we've got those two different setups. So it doesn't matter where you put your origin, put it at the most convenient place mathematically for you. Because notice that wherever you place your origin, that mass itself cancels out because it's 0 units from the origin. All right, so it helps you out that way. Let's take a look at 2 dimensions now. So now instead of just 2 masses, let's go ahead and have 3. We're going to have mass m here, and let's say down here we've got, let's actually give some numbers this time. How about that? Let's say this guy's 3 kilograms, and down here we've got 2 kilograms. They are separated by 2 meters. And let's have another corner of the square over here with a mass of 2 kilograms. And let's say these guys are separated by 2 meters as well. And we want to find the center of mass of the system. Now, x center of mass is again equal to all the xi times mi, those individuals times the total mass. We can say the exact same thing for the y coordinate of the center of mass. It's all of the individual y's, the distances, come on, right, y's, times the individual masses divided by the total mass. Okay, so first you're going to find the x center of mass, then you're going to find the y center of mass, and you can pinpoint the coordinates. Now, you got to pick your origin, as always, so probably makes the most sense this time to pick our origin right here, 0, 0. So let's first find the x center of mass is equal to, let's see here. So first for this mass right here, we have 2 kilograms times 0, because he's 0 units away, 0x units away. And then over here, we've got this guy. He's also 2 kilograms, and he is 2 meters away. And now we take this 3 kilogram mass, but notice that the 3 kilogram mass is still at x equals 0. So we have plus 3 times 0. The x-coordinate of that 3 kilogram mass is still 0. And we're going to divide this by the total mass of the system. 2 plus 2 is 6, plus 3 is 9 kilograms. So we have an x-coordinate of the center of mass is equal to 0, 0. We have 4 divided by 9. 4/9 meters. So it's positive 4/9, which is a little bit less than a half. So 4/9 meters, we're like right there for our x-coordinate on the center of mass. Now we need to find the y-coordinate of the center of mass. So the y-coordinate of the center of mass is equal to, let's start with this guy here, it's 2 times 0. Then we'll go over here to this guy. He's also on y equals 0, so he's 2 times 0. And we've got this guy up here now. He is going to be 3 times 2, because he's 2 units away. Dividing that, or at y equals 2, sorry. Dividing that by the total mass of the system, which is, wait a minute, 2 plus 2 is 4. 4 plus 3 is 7. Totally messed that up. 4/7. 4/7 now is a little bit over 1/2. So we'll still say that's the x-coordinate. The y-coordinate, 7 here. We've got 2 times 0, 2 times 0, 3 times 2 is 6. So we've got 6/7 meters in y. So 6/7 meters, that's almost 1. So we're like right there. So putting the x-coordinate and the y-coordinate together, we are at the point 4/7, 6/7. And that is our center of mass. And the unit here is meters. So the center of mass of this system is that, oh, let's make it green. Green dot right there. Which pretty much makes sense. It should be a little bit closer to the 3 kilogram, not as quite as close to the 2 kilogram over here. We're somewhere in the middle of all 3 of those dots. All right? Now let's take a look at center of mass of solid objects. For solid objects, we get to take advantage of the fact that, let's say we'll take advantage of symmetrical objects when they're presented to us. So for instance, if we've got a solid object that's a square, then we know that if it's uniform mass distribution, the center of mass is going to be at the very center of the square. Halfway on one side, halfway on the other side. If we've got a circle, we know that the center of mass is going to be right in the middle of the circle. If we've got a rectangle, then we know that the center of mass is going to be half the width, half the height. Boom, right there in the center. So these regular shaped objects don't present much of an issue in finding the center of mass. What does then present an issue is when we have combinations of these regularly shaped objects. So for instance, if we take one rectangle here and we add another rectangle here, this might be how we model a hammer or an axe. And you want to throw this axe that way, it's going to rotate around the center of mass. You want to know what that center of mass is. Piece of cake, find the center of mass of one rectangle, find the center of mass of the other rectangle. Now treat them as point particles, with all of the mass of this rectangle centered here at its center of mass, all of the mass of this rectangle here centered at its center of mass. So now you've basically got 2 point particles. You've got this guy here of mass m1, and you've got this guy up here of mass m2. Pick an origin. It might be this guy right here, and find the center of mass in the exact same way that we found the center of mass previously. So let's take a look at an example like this. So let's say we have a rectangular board, and that rectangular board has units of 2 meters on one side and 6 meters on another side, and it has a total mass equal to 10 kilograms. And attached to that board is a square board that is 3 meters on a side, and it has a total mass of 12 kilograms. What is the center of mass of this system here? So we know already that the center of mass of the rectangular board is going to be here at 2,6. And we know that the center of mass of this guy is going to be at 1.5, comma 1.5. And those are not absolute coordinates. That's just, and I totally messed this one up anyway. This should be 1, comma 6. So this is a unit 1 meter away, and this guy is 3 meters away. Yeah, I messed up both of those, didn't I? Don't believe me. It's 1, comma 3. All right, so there's his center of mass, and this guy's going to have a center of mass here of 1.5 units in and 1.5 meters up or down. All right, so we want to find the center of mass of this system. Normally in the book, they're going to tell you what they want you to find the center of mass in reference to. So they might say, find it in reference to this point right here. Make that 0, comma 0. They might say, find it in reference to the center of mass of this guy. All right, I'm going to go ahead and redraw this so that it doesn't look so ugly. So we've got, again, our center of mass here. That is 1 unit, 1 meter over, and it's 3 meters down. And our center of mass here of the square, 1.5 meters over or down and 1.5 meters over. Okay, so let's find the center of mass of this system with respect to this lowest corner over here. All right, so that's our origin, 0, comma 0. So we treat all of the mass of the rectangle being centered here, so 10 kilograms is centered right there, and all of the mass of our square, 12 kilograms, is centered at that point right there. So we just have 2 point masses to deal with. So the x center of mass is going to equal the total mass of the rectangular board times his x coordinate with our new coordinate system. So he's 1 unit over right here. So he's at an x coordinate of 1, plus the total mass of the square, 12 kilograms, and he's a total distance 2, plus another 1.5 right there. So that's 3.5 meters over. And we're going to divide that by the total mass of the system, which is 22 kilograms. So we've got 10 plus, let's do some calculator work here. So it's going to be 10 plus 42 divided by 22. So we've got 52 divided by 22, and we get a total x center of mass of 2.36. So we're 2.36 meters to the right. So we're actually somewhere over here on the square, XCM. Let's do the y center of mass as well. The y center of mass is going to equal the total mass of the rectangle, which is 10, times the y coordinate of his center of mass, which is he's up 3. So 10 times 3, plus the mass of the square, which is 12, times the y coordinate. He's only up 1.5. And we'll divide by the total mass as well, 22. Calculator work. I get y center of mass is equal to 2.18. So 2.18 meters up. So our y center of mass, if that whole distance is 3, we're somewhere like right here for the y center of mass. So putting those together, x center of mass, y center of mass, the center of mass of our entire system is right there, which makes sense kind of intuitively. All right, so we can get the coordinates of our x and y by treating them separately. And it doesn't matter how many objects you've got. You just treat them all as little point masses with all of their mass concentrated at the center of mass, and you just find them the same way. Add up their mass times their distance, mass times distance plus mass times distance, divided by the total mass. Piece of cake. All right, let's put it to practice in class.